Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. We are starting a deep dive into Unit 4, moving charges and magnetism, specifically focusing on a really fundamental interaction, the forces between two parallel currents. Our mission today is simple. We'll break this down so clearly that you'll understand the physics behind the formula, not just, memorize it.
That sounds perfect. We've spent some time understanding how a single wire with current behaves in an external magnetic field, say from a big magnet.
Yes.
But what happens if we take away that magnet and just bring another current-carrying wire close to it? That's where it gets interesting, isn't it?
Exactly. And that's where the curiosity hook really is. Just think about those huge high-voltage power lines you see outside the city.
The ones on those massive metal towers.
Right. They're strung up so high, and often they're several meters apart. If they're just carrying electricity, why does their physical separation matter so much? Why not just bunch them closer together?
I always assumed that was just a safety thing, to prevent them from touching and causing a short circuit. Or maybe for insulation purposes.
That's part of it, for sure. Insulation is critical. But engineers also have to account for a very powerful, unseen mechanical force. A force that pushes or pulls those wires based entirely on the direction of the current.
Wait, really? The current itself generates a force large enough to affect those huge, heavy cables.
It absolutely does,
Yeah.
especially with the thousands of amperes they carry. And here is the truly surprising fact, the one that really goes against what we learned in electrostatics. In electrostatics, like charges repel, correct?
Yes, positive repels positive.
Well, with moving charges, the rule flips completely. Get ready for this. Parallel currents attract, and anti-parallel currents repel.
Parallel currents attract. That feels so counterintuitive. It's like saying two north poles should pull each other closer. Why does the behavior just flip when the charges start moving?
That is the beautiful mystery of electromagnetism we're unpacking today. The force is no longer a direct charge-to-charge thing. It's now a force mediated by a magnetic field, and that changes everything. So let's trace the logic. It's a very simple two-step process. This is the chain of cause and effect you need for the exam. Step 1. Any wire carrying a current, let's call it wire 1, is just moving charges. And we know that moving charges create a magnetic field, let's call it B1, that circles around the wire.
Okay, so wire 1 is the source. It creates the field.
Precisely. Now, step 2, we bring in wire 2, which also has a current, I2. We place this wire inside the magnetic field, B1, that was just created by wire 1. So what happens to a current-carrying wire inside a magnetic field?
It experiences a force, the Lorentz force, F equal IL cross B.
There you go.
So it's not some new magical force. It's just wire 1 makes the field and wire 2 reacts to that field. It's just applying the concepts we already know.
You have understood it perfectly. And because wire 2 also creates its own magnetic field, it exerts an equal and opposite force back on wire 1. It's completely mutual. It's a perfect example of Newton's third law in action. Bridging mechanics and electricity.
That makes so much more sense.
Now, to make this attraction-repulsion rule feel more natural, let's use an analogy. Let's call it the swimmers in a current model. Imagine two swimmers moving in the same direction, parallel to each other, in a pool.
Okay, I can picture that, side by side.
As they swim forward, the water flowing between them, the dynamics of that little channel of water, it actually creates a zone of lower pressure right between them.
A bit like the Bernoulli effect.
Exactly like that. So you have low pressure between them and higher pressure on their outer sides. What does the higher pressure on the outside do?
It would push them inwards, towards each other.
It pushes them together.
Yeah.
That's attraction. So parallel swimmers or parallel currents attract.
Wow. That analogy actually makes it feel logical. It's not a mystery anymore.
Now, what if they swim in opposite directions? Anti-parallel. One is going north, the other is going south, right next to each other.
That sounds chaotic. The water between them would be all turbulent and churned up?
It would be. That clashing, turbulent interaction creates a region of high pressure right between them. And high pressure
Pushes things apart. Repulsion. So anti-parallel currents repel because their fields, their disturbances, clash.
You've got the intuition perfectly. Now let's bring this back to those power lines. Engineers are often most worried about repulsion.
Repulsion. So the currents must be anti-parallel. Why would they run anti-parallel currents in adjacent wires?
Well, in AC systems, the direction of current is always changing. And often one wire is a supply line and another nearby might be a return path. So for significant periods, their currents are in opposite directions.
And that creates a massive outward repulsive force. So the towers and the spacers have to be strong enough to handle that constant pushing apart, especially during a power surge.
That's the engineering challenge. The calculation is fundamental for safety. So with that intuition locked in, let's look at the formal insert mathematics. Could you please read out the formal expression for the force per unit length between two long parallel conductors?
Of course. The magnitude of the force per unit length, F, is given by F equals mu naught I1 I2 divided by 2 pi d.
A very neat formula. Let's quickly clarify that. Constant mu naught for everyone. What is it?
That's mu naught, the permeability of free space.
Perfect. It's a fundamental constant that tells us how easily a magnetic field can form in a vacuum. Its value is 4 pi into 10 to the power of minus 7. Now let's break that formula down step by step. Step 1. Wire 1 creates field B1. From Ampere's law, we know the formula for B1 is mu naught I1 divided by 2 pi d.
Okay, B1 is proportional to I1 over d. The 2 pi d comes from the circumference of the Amperian loop.
Spot on. Step 2. Wire 2 with current I2 is in this field. The force on it F2 is I2 times L times B1. We can ignore the sine theta because the field and current are perpendicular.
Right.
Step 3. We just substitute the expression for B1 into the force equation. So F2 equals I2 times L multiplied by mu naught I1 over 2 pi d.
And if we just rearrange that to get the force per unit length, F2 over L, we get exactly the formula. F equals mu naught I1 I2 over 2 pi d. It all fits together.
It's quite elegant, isn't it? But notice a critical difference here. In electrostatics, Coulomb's law, the force depends on 1 by d squared.
Yes, the inverse square law.
But here, the magnetic force depends only on 1 by d.
That is a very common point of confusion. Why does it decay slower with distance?
Because the magnetic field B itself is already proportional to 1 by d, since it comes from a line of current, not a point charge. The force equation just inherits that 1 by d dependence. Remembering this is absolutely critical for your exam. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now, what's truly fascinating, and something you must know for theory questions, is that this exact formula is used to define the ampere itself, one of the 7 SI base units.
That's amazing. So we're defining a fundamental electrical unit using a purely mechanical quantity, a force.
Exactly. A measurable push or pull is a universal standard. This formula provides that standard. So let's get the formal definition. Could you read it from insert?
Yes. 1 ampere is that steady current which, when maintained in each of 2 very long straight parallel conductors of negligible cross-section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to 2 into 10 to the power of minus 7 newtons per meter of length.
And that number, 2 into 10 to the minus 7, isn't random. You put I11, I21, and D1 into our formula, you are left with mu naught divided by 2 pi.
Yeah.
And mu naught is 4 pi into 10 to the minus 7. So mu naught over 2 pi.
It's exactly 2 into 10 to the minus 7. So the definition is built directly from the formula to give a clean number.
Precisely. It all connects. Let's do a quick example. 2 wires, both carrying 5 ampere. They are 1 centimeter apart, so D is 0.01 meters.
Okay, I1 is 5, I2 is 5, D is 0.01.
We plug it into the formula. F equals mu naught, which is 4 pi times 10 to the minus 7 times 5, all divided by 2 pi times 0.01.
The 4 pi and 2 pi simplify to just 2 on top.
Correct. So we have 2 to the 10 to the minus 7 times 25 divided by 0.01. That gives us 5 into 10 to the minus 4 newtons per meter.
That seems like a tiny, tiny force. Why is it so important in engineering?
An excellent question. For 5 amperes, it's tiny, but the force is proportional to the product of the currents. For power lines carrying, say, 5,000 amperes.
The force would be 1,000,000 times stronger.
1,000,000 times stronger. It becomes tons of force capable of bending steel. That's why it matters. Okay, now for the silent killers. The 3 common mistakes that cost students marks.
Let's hear.
First killer, the distance dependence. Students mindlessly write S is proportional to 1 by D squared. What is the correct relation?
It is F is proportional to 1 by D. Inverse proportion, not inverse square, because the magnetic field from a line source is 1 by D.
Perfect. Second killer, confusing the rule itself. On exam day, under pressure, they think of electrostatics. So which currents attract?
Parallel currents attract, and anti-parallel currents repel, just like the swimmers.
You will not forget it. And the third killer is misapplying it to the real world. For those high-voltage lines, the main concern for engineers is often
the repulsive force, because adjacent lines can carry anti-parallel currents, and they have to design the structure to withstand being pushed apart.
You've got it. Remember that application. The separation exists because of that magnetic repulsion. Now, Block this in your long-term memory. A simple anchor. Just remember the phrase. PAR attracts, A&T repels.
PR tracks, A&T repels.
Good.
Simple and effective.
And a physical gesture. Hold your two hands up, palms facing each other, fingers pointing forward. That's PAR for parallel. Now slowly bring them together. That's attraction. In the exam hall, just do that small action and you'll remember the rule.
That's a great tip.
Okay, let's summarize this whole deep dive in 3 exam safe points. Point 1. The core rule is parallel currents attract and anti-parallel currents repel. This is the opposite of what you know from electrostatics. Point 2. The force per unit length is calculated by the formula F by L equals mu naught I1 I2 over 2 pi d. This shows the force is inversely proportional to the distance, d, not d squared. And point 3, this physical measurable force is the basis for the formal SI definition of the ampere, connecting the electrical world to the mechanical one. And before we go, just one final thought for you to ponder. We've established that this magnetic force depends entirely on the motion of charge, right?
Yes, on the current.
Now imagine you were on a train, moving parallel to these wires at the exact same speed as the electrons inside them. From your point of view, the electrons would look stationary.
If they look stationary, then there would be no current from my perspective, and no magnetic force.
Exactly. The magnetic force would vanish. So what force would you measure instead? This very idea that a magnetic force can transform or disappear depending on your motion is the gateway to Einstein's special relativity. It shows that electricity and magnetism are really just two faces of the same coin. Something to think about. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam.com.
Study well, and thank you for joining us for this deep dive into moving charges and magnetism.